Hi everyone, thank you all for coming. I'll talk about deal.II, like Conrad said. Maybe I don't need to tell you what a finite element library is, but for the context of this talk, it's just a way of turning a partial differential equation into a linear system of equations. And we're particularly interested in large systems. And so what you end up doing is iterative solvers with some kind of multigrid method to be optimal in complexity. You basically have two choices. Either you assemble a matrix and use something of an algebraic multigrid kind, which is, I consider this from the finite element point of view, a black box approach. You have some tuning parameters and it kind of works, and sometimes it works very well. But it's somewhat challenging for adaptively refined measures, for high order and other problems where you don't have a lot of tuning options. The alternative is that you don't assemble your matrices, but that you do things on the fly. And then you cannot use algebraic multigrid methods because you don't have a matrix anymore. Regardless of these two approaches, I will go into a bit more detail in a minute, you have a linear system to solve. So what is deal.II? Deal.II is a community project to solve all kinds of finite element problems. It's a C++ library developed over 25 years or more. I'm one of the 13 developers, and there are thousands of papers that we know of, mostly in academia, of people using deal.II for their science. Don't have to go too much into the features. And I'm interested in basically, I'm part of the effort to put Kokkos into it to have a story on solving things on GPUs. Here are pictures of some of the applications that I'm not involved in everything, but in some of them. So there are various kind of applications codes that solve all kinds of problems. And there's also, of course, because it's heavily used in academia, a lot of numerical methods research is also done inside deal.II. So I thought I should put the slide in to basically tell you where is Kokkos used right now inside deal.II. So it is a required dependency. We bundle a version of Kokkos, and so everybody has it. If you use a certain kind of vector type to store your solution vectors, internally there's a Kokkos view in there, and we have a memory space there that we map to the Kokkos memory space. If you use Trilinos, which many of our applications code use, until very recently, this would mean you run with the ePetra linear algebra stack, that is CPU only. But there's a talk later today by Daniel Arndt about moving to tPetra and how that works, so moving to device. We also have many applications use PETSI, and we've heard about this already. PETSI can, under the hood, use Kokkos or directly one of the vendor libraries, and it's very easy to use and runs on device. And what I would like to talk about today is also a Kokkos-based framework that we have built and that we're in the process of building, and I'll show some early numerical results, to run matrix-free methods inside deal.II that are built on Kokkos routines. We also have support for ArborX. I don't know if people that use deal.II have used ArborX on device, but I know ArborX uses Kokkos and has device support. So these are the different ways how you would interact with Kokkos using deal.II. But as a user of deal.II, you're not directly exposed to any Kokkos internals, and I'll show that in a minute. So here's an example of how this would look like. Aspect is one of the deal.II applications. The two boxes on the left is what typical large applications do right now. Either you do a matrix-based assembly with using ePetra and use something like ML or Mulo, or use a matrix-free framework that we have been developed over the last decade that is CPU only. And the two green boxes is something that are early prototypes that I'm showing you some results in a minute, that can run on GPUs because they're building on Kokkos. So one is using PETSI and Hyper directly with assembled matrices, and the other one is the matrix-free portable framework that is basically a re-implementation with different design decisions having to be made to be running efficiently on device. I have not run tPetra or Mulo on device. I know this is possible, but I don't think anybody has done it inside deal.II, but this is, of course, an option that is also not too far away. And so I will go quickly through this, what the challenges are to run geometric multigrid, because I don't have a matrix anymore. I need to do geometric multigrid. So you directly construct a hierarchy of meshes that you use and that you define your operator on, and then you define your multigrid v-cycle on that. And you do all the operations as matrix-free evaluations. And so this is done on the CPU using vectorization and taking advantage of the tensor structure of the finite element space and of the quadrature points, etc., to be able to gain good performance. And it turns out the higher the polynomial degree, the more it is worth it to go matrix-free, because sparse matrices are very inefficient to go to higher order, have many couplings. And the approach we take is we vectorize with SIMD over n cells at a time, which is not enough to run on a GPU because you have in the order of tens of thousands of cells or something like this. That's not enough. Handling adaptive mesh refinement is somewhat challenging in geometric multigrid. There are several approaches that have been tried in the literature that we have tried in deal.II. It turns out that one of these is significantly faster for many of our applications. We have done this for complex applications. So again, the mantle convection code aspect that I would like to quickly show. So this is a variable viscosity Stokes problem. You have large viscosity variations, and you need block solvers and preconditioners, etc. And this is used in production by scientists to do research into geoscientific behavior. This was work done by Conrad while he was at Clemson with me. So he produced these pictures. These are weak and strong scaling on Frontera up to hundreds of billions of unknowns and hundreds of thousands of MPI ranks. And this works very well. And the punchline at the bottom is we see really good weak and strong scaling for these kind of problems. And typically up to 10 times faster, 1/10 of the memory requirement, and better scalability on the small side and the big side versus the assemble a matrix, put it into an ePetra CRS matrix and run ML. Of course, also with block preconditioners, etc. So that's the power of the matrix-free approach, and that's why we have been working for many, many years to now, how can we actually bring this over to a GPU, because it doesn't translate one-to-one. But this works, and so we just have to adapt this. So GPUs, it's very easy with something like PETSI. You can just say, please move this to the device. Hyper works on device, and it produces something. And the question I had coming into this is, well, this is super easy, but how fast is it actually? Is it actually useful? I haven't tested Mulo, like I said. And then we basically wrote a new matrix-free interface that includes a geometric multigrid, so it contains grid transfers and smoothers, and all these operations that you need to build this. It's built on Kokkos. We need more fine-grained parallelism. So what we do is basically you do a loop over cells, and then within the cell you have an inner Kokkos parallel for that does like one-dimensional integrals, and then that are summed up over the quadrature points or one-dimensional degrees of freedom if you have a tensor product structure. And that gives you enough parallelism to actually run on device and be fast. This is still early, but I'll show you some of the early results. This is, of course, not my work, but the work of many people who have been involved in this. Daniel and Bruno are sitting in the room back there if you have more questions. And so this is a very simple test problem, also motivated by the earth science application, but this is just a variable viscosity Stokes variable viscosity Laplace problem posed on somewhat complicated geometry with adaptive refinement, with large viscosity ratios, etc. But it's Laplace, so it's a bit easier to do. The machines I'm looking at is an AMD workstation and an NVIDIA H100. Depending on how you compare, if you compare dollar price, they are very different. If you compare watt, they're very similar. If you compare FP64 performance, they are somewhat different, at least theoretical peak performance. But that gives you maybe an idea of how to compare these two numbers, right? And so what I'm going to do is I'm going to show you, going from left to right, the highly optimized matrix-free geometric multigrid that is only CPU implemented. Then I compare this to a matrix-based approach using PETSI and Hyper on the CPU. I'm also I realized how bad the results are when I go to higher order finite elements. And so there are several approaches that you can do. That's the picture on the right. You can do a low order rediscretization. So you basically interpret your high order finite element space as a linear finite element space on a finer mesh, and then you just hand this to an AMG and solve that and use that as a preconditioner. That's been made popular by the MFEM library. And what I also tried out is, how about I do it the right way? I use the same mesh, but I use a P multigrid to go from quadratic or whatever element that I want to solve on to linear elements and then use AMG there. The advantage is, of course, that AMG matrix is much smaller, which means it can run much faster, right? Especially for higher order than quadratic elements. And so then I compare these different approaches and see where the performance is and what that looks like. So, operator evaluation. So this is just computing for a given input vector Laplace of u, basically, right? And so the surprising thing that you see is that, so this is a throughput plot, and on the x-axis is polynomial degree from linear, quadratic, cubic, fourth order degree polynomials. You see that, maybe it's obvious to you, but memory bandwidth is much higher on a modern GPU. So matrices for low order run very fast. Whereas if you look at the two solid lines, as soon as you go from linear to quadratic elements, the matrix-free implementation is much faster, even though this is the simplest PDE I can write down, right? It's a scalar, simplest equation that you can actually evaluate the operator with, right? And if you look at Q4 going from blue to red on a CPU, that's the up to a factor of 10 faster that I see in practice, right? And so the GPU is a tiny bit faster, and so our portable matrix-free in green works very well and beats the matrix-based one at some point, right? The trade-off point is at a different point. So the lower order works better on GPUs than it does on CPUs. This is something that I didn't know coming in, but it's interesting that it actually means that if you can live with low order, then assembled matrices, sparse matrices are actually quite good, and hyper seems to be optimized, and PETC seem to be optimized well to do that. But that's not the whole story. This is just multiplying a matrix, right? When you do a solve, you need a preconditioner, right? So you need to do either algebraic or geometric multigrid. So again, this is throughput. This is only on the CPU. And here you see that even though they were somewhat close, our matrix-free CPU approach is way faster than the matrix-based approaches. But the low-order discretization is certainly worth it, right? So there's no much effort here. You have a significantly faster, you need less memory, and you have a much faster time to solution. And that's not very difficult to do, and something people should at least consider when they do this. I didn't know that ahead of time either. So this is on the CPU, right? Matrix-free wins for everything except linear elements by a large margin. So how does this look like on the GPU? Maybe we start with the solid lines. So at the bottom, the blue one is just matrix-based hyper AMG that gets worse and worse with higher order, right? If I do any of the solid yellow and red lines, that's the low-order AMG, or matrix-free operator evaluation and low-order AMG. They work much better for higher order, right? But they obviously stay in the same bound performance line. But then to the dashed lines, so this is our matrix-free framework, either with a geometric multigrid, H multigrid, or going down polynomial degree, and then the tiny problem is then tackled with AMG. They both are significantly faster, right? As you can see. One could think about comparing this CPU versus GPU. That's maybe not that interesting because it depends on what devices you compare, but per watt, the performance is somewhat similar at this point. And again, maybe I should stress all of this is very early and there's a lot of optimization and bug fixing and things that needs to happen. And maybe this plot is a bit busy, but so let's ignore that and not put too much weight into like the actual numbers here. This is a slide by Ivan from the University of Bochum, who also works on deal.II. This is showing on the Jupyter system, that's a European Grace Hopper system, showing this matrix-free framework. So he does P multigrid and H multigrid, scaling, weak scaling. On the right is the solve, on the left side is just the matrix vector product scaling to a few hundred GPUs. So that works. There's a lot of stuff to do to optimize and whatever, but we can certainly already solve problems that are very large. The other thing that we're doing, which kind of ties into the last talk that we saw about the Moose framework, I'm not sure how readable this is, but we are trying to have the difficult task of, the problem is that the PDE is defined on the user side, and deal.II is a library, but we don't want to expose any of the Kokkos internals. And so the way it works is, at the very top left, so this is the portable matrix-free Laplace operator. And this is somewhat pseudocode here. I deleted a lot of stuff to fit it on a slide. But basically what the user says, if I want to do a matrix vector product, I'm calling and I say, I would like to do a cell loop, right? And I'm giving you the local operator on the cell, what to do. So that calls into the deal.II library the cell loop function, which does a bunch of stuff, which moves stuff to the GPU, pre-allocated inverse Jacobians and other information on the cells, etc. Package this up into shared memory and does basically Kokkos parallel 4 with this kernel thing that wraps this functor, and then that calls back into the user code. So the user code now has a cell operator, right? And so this cell operator gets executed in parallel. There's a bunch of stuff that happens. What do you need to do for a finite element method to do a matrix-free evaluation? You basically have to read the values from the global vector. You have to evaluate, for example, gradients to compute a Laplace, right? And then you have to actually define what happens in each quadrature point. For that, we basically have a thing that's called for each quad point, which calls back into deal.II. Right? And inside the deal.II library, there's now a team thread range of this inner parallelism within a cell, right? That already has a functor again, and that functor calls back here, in this case, into this lambda. And there you can see submit gradient of get gradient. This is gradient of grad u, right? That's Laplace of u. That's how the operator is implemented. So if you had a variable coefficient, if you had other terms, this is where they would go, right? And so, of course, I'm hiding a lot of stuff here, but so for example, the evaluate and the integrate ones need to do like these inner kernel launches for the one-dimensional integrals to then package them together into the three-dimensional integral, et cetera, et cetera. I'm not going to show you this here because the point of this slide was to show you that the user basically says, I have a cell loop, these are my finite element variables, and this is the weak form basically that I would like to integrate on the fly. And this is all that the user needs to do to run on device, right, or multiple devices or whatever. Yeah, and so I wanted to spend a minute to talk a little bit about my experience adopting Kokkos. I think these are the right abstractions. So for example, a parallel 4 and parallel reduce. I know this is very easy from the Kokkos developer side of things, but I was scared away when I first saw I was researching, trying to understand GPUs, like what do you have to do to make a parallel reduce run fast? Right? This is way too complicated in application codes to expect anybody to know what to use except the domain experts. And I think this is amazing. The real cool thing is that I can let my students watch a couple of Kokkos tutorials and they can contribute. They can contribute to code that runs on GPUs. This would not be true if I had to teach them all the CUDA internals. So I also count myself in there because I started contributing to this Kokkos backend without knowing all the details, right? Fixing bugs, improving, adding new features, etc. That wasn't that difficult. A big selling point, I think, is that all the contributions we made were immediately run and compiled by everybody who uses deal.II without them knowing, right? So we immediately have the CI coverage and everything. It's not like there's some GPU stuff somewhere that nobody touches and that gets out of date, right? It's immediately there and it's incrementally tested and improvable. And it is a pleasure to develop things without having to develop on a GPU, right? Faster compiles, easy debug experience, all of this is amazing. And then the surprise that it works on the first try if you actually go to a device. And it doesn't matter, right? I experimented with all the device vendors and all of this basically works after you get it to run. So I'm really happy about this. And I think it was a great decision for deal.II to actually build on Kokkos in this way. And with that, I'll conclude in short. deal.II can run on GPUs now. We can do matrix-based and matrix-free approaches. We are somewhat fast. We can run on clusters. And it's like a decade-plus effort to develop matrix-free solvers. And they seem to also work competitively on GPUs, even though the trade-offs for matrices are different. What I didn't show you is, of course, matrix-free has many other advantages. For example, you can solve 10 times larger problems on a GPU because you don't need to store any matrices, even for linear elements. And then also what I'm very much interested in, that's why I'm asking questions about this earlier, is like mixed and lower precision support. With modern GPUs, that's very important. I can give you a number. If I run my geometric multigrid V cycle in single precision and my outer Krylov CG solver in double precisions, you get about a 2x performance speed for no for no loss in accuracy, right? And we want to do a lot more in selectively reducing accuracy. So there's a lot of work left to do, but I'm very happy and proud that we're at a point where it is actually usable. Thank you.
I have always seen basically higher throughput at a higher order. Could you go back to your slide on Laplace as a function of order? Laplace throughput.
Yes. So
can you speak to the quadrature that you're using at each order here? Is it the same? Is it dependent on the order as well?
So you do see a big improvement if you go from left to right, for the matrix-free methods in throughput. Yes, it improves with higher order, for sure. And this is normalized this is throughput per degree of freedom, right? So you actually get a lot more accuracy for higher order, and you get higher throughput, right? Because you're somewhat bandwidth limited. You're streaming in a vector of coefficients, and it doesn't matter that it's a higher order element. So yes, for matrix-free methods, you get higher throughput for higher order, and that's what expected.
Sorry, what is the yellow curve?
That's just PETC matrix, matrix vector MV for matrix space, sorry. Yes, for matrix space, you get a lot more entries per row, and so the performance drops for higher order. But on a GPU, the linear elements work really well, surprisingly to me, because of high memory bandwidth, right?
All right. If you want to go ahead. I might have missed this, but do you expect the end users to, for geometric multigrid, do you expect the end users to have different levels of meshes, or how do you interpolate, or do you interpolate that on the fly?
Yes, so you have to have a hierarchy of meshes.
Okay.
The way it's done in deal.II is you typically run on a coarse mesh and you refine it.
Okay.
Right? So you import a low resolution mesh like a spherical shell, and then you refine it 5 times, and that's your multigrid hierarchy. If you don't have that, there's no good way to do geometric multigrid.
Okay. Thank you.
At least not in the mesh.
Do you use separable compilation?
Oh, I'm sorry. Say that again, please.
Are you using separable compilation? Were you using the NVC wrapper to compile the full deal.II? Or?
We compile the full deal.II, we configure with Kokkos, and we use the host compiler for everything. Yeah.
How much slower was it when you went to CUDA compared to not having this?
So that's why I love Kokkos, because I can develop with just using the host compiler, and if I need to run it on a GPU, I don't care about the compile speed. NVCC is like a factor of 3 or 5 slower or whatever, so that's painful, but if I don't have to do this every few minutes, then that's fine.
Thank you.